We discussed the methods for the determination of oxidation number or oxidation state. Now, what is oxidation and reduction in terms of oxidation number? Oxidation, an increase in the oxidation number of the element in the given substance. In the given substance. For example, you consider the reaction between magnesium and oxygen. Magnesium combines with oxygen to give magnesium oxide. In the elemental state, the oxidation state of magnesium 0, and in magnesium oxide, oxidation state of magnesium +2. So here we can see an increase in oxidation number, the case of magnesium, 0 to +2. So magnesium is oxidized. So oxidation, an increase in the oxidation number of the element in the given substance, even though it is in the free state, elemental state, or if it is in the compound, you have to check the oxidation state or oxidation number. And if it is increasing as we move from reactant to product side, that substance or that element is oxidized. Similarly, what is reduction? A decrease in the oxidation number of the element in the given substance. That is reduction. So in the previous example, magnesium plus oxygen gives magnesium oxide, oxygen in 0 oxidation state in the reactant side. And in the product side, the oxidation state of oxygen -2, 0 to -2, decrease. So oxygen is reduced. Now different types of redox reactions. Redox reactions can be classified into 4 types. The first one is combination reaction. As the name indicates, we can see the combination of 2 elements to form a compound. So here carbon and oxygen combines to form carbon dioxide. 2 elements combines to form carbon dioxide. A combination reaction. Magnesium and nitrogen combines to form magnesium nitride. A combination reaction. And these are redox reactions also. Here carbon is in 0 oxidation state. Here carbon in +4 oxidation state. 0 to +4, an increase in oxidation state. Therefore carbon is oxidized. Oxygen here in 0 oxidation state. Here -2 oxidation state. A decrease in oxidation state from 0 to -2. Here oxygen is reduced. Similarly, here magnesium 0 to +2 oxidized, nitrogen 0 to -3 reduced. Another example for combination reaction, CH4 and O2. These 2 combines, but here there are more than 1 products. So these are combination reactions. If there is combination, surely there is decomposition. So next one is decomposition reactions. Examples, H2O decomposed to give H2 and O2. We know it is happening in electrolysis, isn't it? H2 in H2O, hydrogen in +1 oxidation state, oxygen in -2 oxidation state. And when it decomposes, both changes to elemental form, H2 in 0 oxidation state, O2 in 0 oxidation state. So +1 to 0, hydrogen reduced, -2 to 0, oxygen oxidized. NH decomposed to give Na plus H2. +1 to 0, sodium reduced, hydrogen -1 to 0, hydrogen oxidized. Next one is displacement reactions. What is meant by displacement reaction? One atom is displaced by another, or one element is displaced by another element. That is displacement reaction. We can identify 2 types of displacement reactions. The first one is metal displacement. Already we discussed it in competitive electron transfer reactions. reaction between copper sulfate and zinc. Zinc displaces copper from copper sulfate. So you will get copper plus zinc sulfate. Zinc displaces copper from copper sulfate. So here copper in +2, but in the product side it is in 0 oxidation. Decrease in oxidation state, reduced. Zinc is 0, here it is in +2, oxidized. Vanadium pentoxide when treated with the calcium, vanadium is displaced by calcium. Vanadium plus calcium oxide. Metal displaced, metal is displaced. Here, metal from this compound displaced. Here, metal from this compound displaced. Metal displaced. Similarly, there is non-metal displacement. Non-metal displacement reactions. Sodium plus H2O. Here, hydrogen is displaced by sodium. NaOH plus H2. H2 is removed. Hydrogen is displaced by sodium. Calcium displaces hydrogen. CaOH2 is plus H2. Chlorine displaces bromine. KCl plus Br2. In all these reactions, you can see there is oxidation and there is reduction. So all these are redox reactions. The last one is disproportionation reaction. Disproportionation reaction. What is disproportionation reaction? The same compound is undergoing oxidation and reduction, or the same element is undergoing oxidation and reduction. That is disproportionation reaction. In a disproportionation reaction, an element in one oxidation state is simultaneously oxidized and reduced. An element in one oxidation state is simultaneously oxidized and reduced. An example, decomposition reaction of H2O2. 2H2O2 gives 2H2O plus O2. Here hydrogen in +1 oxidation state, oxygen, since it is a peroxide, -1 oxidation state. Here oxygen in -1 oxidation state. And in H2O, hydrogen in +1 oxidation state and oxygen -2 oxidation state. In oxygen, it is elemental state. Oxygen is in 0 oxidation state. Here we can see oxygen in the -1 oxidation state is oxidized to oxygen in 0 oxidation state. At the same time, oxygen in the -1 oxidation state is reduced to oxygen in -2 oxidation state. It is a disproportionation reaction. Now, an application of redox reaction. Redox reactions can be used for the volumetric estimations or quantitative analysis. There are different types of redox titrations. Redox titrations. Here we can see 3 of them. The first one is permanganometry, then dichrometry, and the third one iodometry or iodimetry. Iodometry or iodimetry. And here in the titration, dichrometry or in permanganometry or in iodometry, we are using a redox reaction for the estimation of solute present in the given solution. First we can see permanganometry. In permanganometry, we know potassium permanganate is an oxidizing agent. Acidic potassium permanganate is an oxidizing agent. Fe2 plus, that will undergo oxidation, or it is a reducing agent. Fe2 plus can be oxidized to Fe3 plus. So for the estimation of Fe2 plus in a solution, we can use permanganometry. Permanganate is pink in color. As it reacts with the Fe2 plus, when you add permanganate to a solution containing Fe2 plus, its decolorization will take place. As the permanganate reaches in the solution of Fe2 plus will be oxidized to Fe3 plus, and permanganate ion, MnO4 minus, will be reduced to MnSO4. So immediate decolorization will take place. But when all the Fe2 plus is reacted, or when it is completely reacted, you will get a pink color in the compound. You will get a pink color in the compound, in the solution. Or the pink color of permanganate ion will, you can see that pink color of permanganate ion. That is the end point. So here potassium permanganate itself acts as the indicator. Or we can say potassium permanganate is a self-indicating solution. In your practicals, there is permanganometry, then it will be clear to you. And the second case, dichrometry. The dichromate is colored, but that is not enough to identify the endpoint of the reaction. When we use dichromate, potassium dichromate for the titration, we cannot identify a color change if we use dichromate for the titration. Potassium dichromate also an oxidizing agent. Fe2 plus can be estimated using dichrometry, means titration with the potassium dichromate. And if the endpoint is not clear, in such cases, we can use an external indicator. And here, diphenylamine is the indicator. When all the Fe2 plus is converted to Fe3 plus, the next drop of dichromate impart a blue color to the diphenylamine. Thus, we can identify the endpoint. In the last case, iodometry. We have to identify an ion which will react with the I minus, and I minus will be oxidized to I2. So Cu2 plus can oxidize I minus to I2. So for the estimation of Cu2 plus ions, we can use iodometry. When potassium iodide is added to Cu2 plus ion solution, what happens? Iodine will be liberated. That liberated iodine will react with the sodium thiosulfate, hypo. So if there is Cu2 plus, surely iodine will be liberated, and that it will react with that iodine, sodium thiosulfate. And when all the copper is reacted, what happens? The liberation of iodine stops. So the end of the reaction can be identified by the addition of starch to the solution. If there is iodine, starch will give a blue color. Starch will give a blue color. So it is another type of redox titration. Next application is in galvanic cell. All of you are familiar with the galvanic cells because in the lower classes you have studied it. Electrochemical cell is a device which converts chemical energy of a redox reaction into electrical energy. That is also known as galvanic cell or voltaic cell. So galvanic cell is a device which converts chemical energy of a redox reaction into electrical energy. Here we can see zinc copper cell or Daniel cell. It is the anode compartment of this cell. Here, it is an electrolyte solution containing Zn2 plus ions. Can be SO4. This zinc rod. Here it is copper rod and it is immersed in Cu2 plus ion solution. It can be copper sulfate. It is a salt bridge. It gives an ionic contact between anode compartment and cathode compartment. Actually, it maintains the flow of current in a galvanic cell, the salt bridge. When zinc is immersed in Zn2 plus ions, it has a tendency to lose electrons, and that tendency is known as oxidation potential of zinc. So surely zinc releases its electrons and will change it to Zn2 plus and enters into this solution. And the released electrons will pass through this circuit and reaches here in copper electrode and passes into the solution. There it combines with the Cu2 plus to form copper. So here zinc is oxidized to Zn2 plus, and here Cu2 plus is reduced to copper. Here oxidation, here reduction. During oxidation, release of electrons, and that electrons are consumed here. So after the removal of electron, here Zn2 plus will be excess in this compartment, so positively charged. After the deposition of copper from Cu2 plus, SO4 2 minus will be present here, a negatively charged ion. So here excess negative charge is present. So further flow of electron impossible. Why? It is not possible to take electron from a positive solution. Similarly, it is not possible to give electron to a negative solution. So for the neutralization of the charges in the electrolyte solution, we will use this salt bridge. The electrolytes present in the salt bridge like KCl or KNO3 will neutralize the charges in the anode compartment and in the cathode compartment. After neutralization, what happens? The continuous flow of electrons occurs. Thus, it will generate electricity. So what is the anode reaction? Anode reaction is the oxidation of zinc. Zinc gives Zn2 plus 2 electron. And what is the cathode reaction? Cu2 plus 2 electron gives Cu. The cell can be symbolically represented as Zn bar Zn2 plus double bar Cu2 plus bar Cu. Here we can see it is oxidation reaction. Zn gives Zn2 plus. And it is reduction reaction, Cu2 plus bar Cu. And this double bar represents salt bridge, ionic contact between the anode compartment and cathode compartment. It is the UPSC representation. And what is cell reaction? It is the total reaction in the cell. If you add anode reaction and cathode reaction, you will get cell reaction. Zn plus Cu2 plus gives Zn2 plus Cu. That is the cell reaction. Electrode potential. What is electrode potential? That is the potential associated with each electrode. Maybe oxidation potential or reduction potential. What is oxidation potential? It is the tendency of an electrode to give electrons when it is in contact with its own ions. And what is the reduction potential? It is the tendency of an electrode to accept electrons when it is in contact with its own ions. That is reduction potential. So for convenience, for the comparison of electrode potentials, we'll take only the reduction potential. So if you simply say electrode potential, that means reduction potential of the electrode. And what is standard electrode potential? Standard electrode potential is the electrode potential measured at standard conditions. That means at 1 molar concentration, 1 atmosphere pressure, and 298 temperature conditions. That is standard electrode potential. Similarly, there is cell potential. What is cell potential? This is the difference between the electrode potentials. That means electrode potential of cathode minus electrode potential of anode. That is cell potential, E cell, represented as E cell, cell potential. There is another term, EMF. EMF is slightly different from cell potential. EMF is the difference in the potential when there is no current. When no current is drawn from the cell. When no current is drawn from the cell. That is EMF. It is the difference between the electrode potentials when no current is drawn from the cell. That is EMF. And cell potential is the difference between cathode potential and anode potential. Standard electrode potential of cathode minus standard electrode potential of anode. Or a reduction potential of cathode minus reduction potential of anode. Okay, it is enough for today, and we can continue in the next class.